Okay, so remember what we didn't know what this boundary layer is? We don't know what that scale in the y direction velocity is for this picture. Right, so this scale is like infinity. I don't know if I have a scale for this v velocity yet. So what value it is? Usually what you say is this terminology. So you say, what does the y velocity scale like? Okay, and if you're ever trying to figure out velocities, right, so if you're trying to solve for some type of velocity in something, that's what continuity is for. So continuity, right, that equation continuity gets you velocity info always. That was said to me a long time ago, and I never forgot it, so I'm just passing that on to you, that you have to think about continuity as the thing that can help you get velocity information. If you know that, you can just kind of go there. So this idea of, right, I don't know what this scale's like. If you had that in your head, you go like, well, continuity always tells me the information about velocity, so I'm going to go to continuity. So remember, a continuity equation was this. So, right, expand it out. Just the definitions. Remember our scales. Oh yeah. And you can say that this velocity is, right, a very tiny number and then one more in and out of the board because it's a flat plate. Imagine that it extends pretty large. So we'll call that capital W. And it's right there where this is a very, very large number. Just like this is a large number as well. The plate goes very far in that direction and very far in this direction. So we do the non-dimensionalization stuff, take our parameters out. So this one we get infinity and L. Okay. Because we've non-dimensionalized these numbers, right? Right? All these non-dimensional differential terms just look like the number 1. So then you go into your scales, right? In fact, this one's just basically, right, this one we don't even care about because this was a tiny number, this is a large number, so that's just like way out of there. So that sort of motivates this two-dimensional flow look for boundary layers. Okay, so they just throw them out, right, a scale equation, right? So then you move this to the other side so that these two terms have to balance. These two terms have to balance, which means this. This is thrown out because this was basically, right, this is basically 0 and this is a large number. So that allows us then, you can see, I can figure out what this is. So that means that this velocity scale is like, which is sort of the very first important concept of boundary layers. Because what is this saying? Right? It's saying something that makes a fair amount of sense. I draw this picture so many times. Right? What is this saying? So u is some large number, right? That's okay. Right? Say if it's an airplane. It's like 500 miles per hour, right? Haven't told you how to get the delta yet, but don't worry about that. But just say you know, right? Just so you understand, you know what this does scale like, and this L. So what's the width of the length of a wing? Maybe that's not 50 feet. I don't know. What do you guys think it is? I'm talking about this. Let's say it's 30 feet. And then I already told you that this is like 1 millimeter. I can tell you why later. But right, so what this is saying is the velocity going this way, a known one, the far field one, was about 500 miles per hour. And this is saying that in terms of my two-dimensional system of velocities I have to solve for, that the y direction one is a small number divided by a super large number, right, times this big number. So it makes sense because it's saying the velocity fields have gotten right in the y direction. So any velocity like going upward is way smaller than the x direction velocity, which makes sense. We don't normally see in external flows fluid just like shooting up off of a plate, do we? No, I've never seen that. Usually it's sort of consistently going that way. I don't see net-like suction happening when I'm just flowing a boat over water or through air, right? We just commonly see that. So that just makes sense here, and that's always a good thing to keep checking up on. But that's the first sort of big thing we derive for this boundary layer, and we just kind of prove it to ourselves that the y direction velocity is just a whole big amount smaller than the far field velocity. So the next part is you sub in now these scales. So let's say the vector now, I know that this thing scales like this. I'll make this 0 because of that. We're just going to say it's 0 velocity because of some reasoning that we came up with. It helps to actually scale the differential operators as well. This is how I do it. Okay, so this scales like this vector. And then lastly, we have to scale the pressure. And what does that scale like? Right, pressure is going to scale like the dynamic pressure of the flow. And you always do that for fast-moving fluids because you're looking at the ratio of inertial terms to these viscous terms. What's the balance of those? So a good pressure to pick of balancing those is a dynamic pressure. So taking these scales and plugging them into the vectorial Navier-Stokes equation, right, which is extra credit, you can derive, right, the non-dimensional term, which I'll write out later.